Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Imagine trying to force a hard metal billet through a tiny die opening. In normal extrusion, the metal fights back. Friction increases, heat builds up, and cracks begin to form. But what if we could remove almost all wall friction? What if instead of pushing metal with a solid ram, we surrounded it with pressurized fluid? This is hydrostatic extrusion. In this process, fluid pressure does the job of the ram. It's a method where brittle alloys can behave like ductile materials, creating precision metallic products. To understand this, we must look at why conventional extrusion fails. When surface friction drags the metal, internal stress causes tearing and chevron cracking in high-strength alloys. This non-uniform flow is the enemy of metallurgy, but hydrostatic extrusion applies compressive pressure from all directions, suppressing crack formation before it starts. The idea was experimentally investigated by Nobel laureate Percy Bridgman. He proved that ductility is not just a material property, it depends on the stress state. Bridgman showed that many brittle materials become ductile under extreme pressure. This scientific insight became the foundation for modern hydrostatic metal forming. Normally, we think of ductility as fixed, but under compressive hydrostatic pressure, internal cracks are suppressed, allowing metals to flow where they would otherwise shatter. Tensile stress pulls atoms apart, growing cracks, but hydrostatic pressure closes them. It changes the stress environment so the metal can flow without fracturing. A hydrostatic system starts with the pressure vessel, the strongest part of the machine. It must contain enormous internal pressure, often thousands of bars. Then there is the pressure medium, usually a special oil or polymer, and the critical sealing system that prevents any leakage under massive pressure. The process begins with precise billet preparation. The chamber is filled with the medium, ensuring all air is removed to prevent unstable pressure response. As the intensifier ram increases pressure, the fluid transmits force uniformly. Once it exceeds the yield point, the metal flows toward the die opening. The billet emerges as a rod, wire, or tube. In advanced systems, a back pressure chamber at the exit prevents any sudden cracking during depressurization. Engineering precision is key. We calculate the extrusion ratio, R. For a 50mm billet becoming a 10mm rod, the ratio is 25:1. The true strain in this case is the natural log of R, giving a high plastic strain of 3.22. This intensity is what refines the metal's grain structure. To estimate pressure, we multiply average flow stress by the strain. A high-strength alloy might require nearly 2,000 megapascals of hydrostatic pressure to flow. These vessels are thick-walled cylinders. Hoop stress is highest at the inner wall, meaning the vessel must be designed using Lahm's equations for maximum safety. Fatigue is a major concern. The vessel undergoes repeated stress cycles. Without perfect engineering, microscopic cracks could lead to catastrophic failure under pressure. Engineers use auto-frettage, pre-stressing the inner wall to improve fatigue life. This ensures the vessel can survive thousands of high-pressure cycles without failure. The seals are survival components. At ultra-high pressure, a tiny leak becomes a high-velocity jet. Self-energizing seals are critical to maintaining system integrity. The die angle is a careful balance. Too small and friction increases. Too large and redundant deformation causes flow instability at the core. By applying compressive pressure from all sides, we suppress central burst or chevron cracking. The high external pressure literally keeps the metal's core together. The metal actually becomes stronger. High plastic strain refines the grain size, and according to the Hall-Petch relationship, smaller grains mean a harder, stronger product. We must manage adiabatic heating. Mechanical work converts to heat instantly. In high-strength alloys, this rise must be predicted to avoid unwanted softening. The pressure medium must be stable. High-pressure oils or polymers are chosen so they don't solidify or chemically react with the billet during the process. While aluminum handles conventional methods, high-performance titanium and nickel alloys are the primary candidates for hydrostatic forming due to their brittle limits. Compared to conventional methods, hydrostatic extrusion offers lower friction and better brittle alloy forming, though at a higher equipment cost. Industrially, it's the gold standard for copper tubing, titanium aerospace components, and ultra-fine superconducting wires for medical and research use. Safety is non-negotiable. With so much stored energy, systems require certified vessel designs, regular crack detection, and remote operation shielding. The future lies in computer-controlled pressure profiles and AI-based defect prediction. Machines will soon engineer the microstructure in real time as they form. It's not just about shaping metal, it's about engineering the internal properties. Hydrostatic extrusion is the bridge between raw alloy and precision component. Hydrostatic extrusion proves that the solution isn't always more power, it's better control. Control of pressure, friction, and the very stress states of matter. Keep learning and keep discovering the engineering behind modern industry. Subscribe to Simple Guyane for more. I'm your host, and I'll see you in the next deep dive. Simple Guyane, simplifying the complex.